Hello everyone, this is the 12.3 lecture video. So in this lecture video, we're going to be talking about dot product. We're going to give the definition, how to compute it, and then we'll see some applications as well. This is a very important tool in mathematics. Um, you can't really go much farther in math without using the dot product extensively. If you guys take linear algebra, 3105, 3106. You'll use it extensively, and then if you went any farther than that, you would just keep on using it. Okay, so let's see. In the previous section, we talked about vector addition and we had scalar multiplication, and we were kind of making these operations, and they're kind of similar to addition and multiplication in just the real numbers, right? We can add two numbers together, multiply two numbers together. Okay, and then we kind of had analogs in the vectors. We can add two vectors together, but then we said that, okay, multiplying two vectors together, well, there's a couple of ways to do it, but we introduced scalar multiplication last time, which was just multiplying a vector by a scalar. Okay, but now I want to talk about one of those several ways we talked about multiplying two vectors together. Okay, so this is going to be the first way we learn to actually kind of multiply, if you want to call it that, two vectors, where we take two vectors and we get some sort of result from combining them other than addition. Okay. So we're going to introduce the dot product, and let's just talk about the mechanics of it first, and then we'll talk about what the dot product really represents. Okay. So the mechanics of it are really easy. And again, this is something that works in higher dimensions, not just R3, and it works in R2. And, you know, if you want to think about multiplying two numbers together as a dot product, you could say this holds in just R1 as well. But this holds in any dimension, really. But we're going to see it a lot in R3, and I'll show a lot of examples in R2 as well, just because R2 is easier to draw. So let's say, let's kind of do our higher dimension example right now, or just an arbitrary dimension. Let's say I have an Rn. So I have a space like this. I'm working in a space like that. So when I say Rn, when I don't give a specific number, that kind of symbolizes that this works no matter what this number is, whether it's R2, R3, R4, 5, 6, 7, 100,000, doesn't matter. Okay. So let's just stick with Rn for now, for just a second. Let's say I have these two vectors in Rn, the vector v and the vector w. Okay, and this vector v has n components, right? We're working in n dimensions, so our vector should have n components. Okay, a1, a2, all the way up to an. Okay. This is just like if I have a vector in 3 dimensions, I have the components x, y, and z, right? Well, if I have n dimensions, instead of trying to write x, y, and z, I usually pick one letter and then just have a number that kind of denotes where we're at. So that's what's going on there. So I have two vectors, v and w and Rn. What is the dot product of these two vectors? Well, it's easy. I just multiply a1 and b1, a2 and b2, and so on, all the way up to an times bn, and then I add those things together. Okay, so I have a1 times b1 plus a2 times b2 plus a3 times b3, and so on, all the way up to an times bn. Okay, so let's see a concrete example, or well, let's see, let's kind of confine ourselves to R3 now, and then we'll see an example. So this is how it looks in Rn, and if you want to be specific, how does it look in R3? Well, in R3, I would have a vector like this, right? A1, A2, A3, which we could, if you're more comfortable with it, we could have said X1, Y1, Z1, or, well, how about X, Y, Z? And then this vector, instead of X, Y, Z, or we could have called it X2, Y2, z2, something like that. I'll use this type of notation a lot just because it's a lot easier than that can x, y, z for me. All right, so let's try and take, what would the dot product of these two vectors look like? Okay, I would have a1 times b1 plus a2 times b2 plus a3 times b3. Okay, so this is just the bare mechanics of how this dot product works. So what's going on? You know, what is the result of this? First of all, if this is just a number, right? This is a number in R. This is a number in R, the real numbers. This is a number in R, right? And then I add those together, and again, I just get a number in R. So I'm taking two vectors, and I'm, you know, if you want to call it multiplying, I'm taking the dot product of them. It's sort of like a multiplication. I'm taking two vectors in R3, I'm taking the dot product, and my result is just a single number in the real numbers in that R. Okay. So now let's see a specific example. Let's try, let's take some specific numbers x for our vector x and our vector y. Okay, so let's say our vector x has these components, y has these components. What's the dot product? So try this, you know, pause, try it on your own. Let's continue. So dot product would be 1 times 0, right? I multiply 1 times 0. Then I add what? -1 times -4. Be careful with your negatives. Okay, then I add 7 times -2. Okay, that's going to be 0 plus 4 minus 14 equals -10. So that's my dot product of those two vectors. Okay. Now let's recall this notation from section 12.2, right? When I have 3i minus 2j plus 6k. Okay, remember what our I, j, and k are. Remember, I is the vector 1, 0, 0, the unit vector in the direction of x. J is the unit vector in the direction of y, so 0, 1, 0. And k is unit vector in direction of z. Okay. So when I have 3i minus 2j plus 6k, what is that vector? That's the same as saying we have this vector. Oh, I don't need the I there. Okay. So you might think this is a much easier way to write this. So why do we bother with this notation? Well, it might seem more complicated now, and in most cases it is more complicated. But this notation will be extremely useful, even in the next section when we're talking about cross product. So this notation will be necessary. So let's just practice with it a little bit now. So this is my vector, right? And what's this vector? How can I write that vector? I have a dot product here. What's this vector on the right side? 1i minus 2k. Well, 1i, well, that tells me I have a 1 here. And then I don't have, there's no j in here, right? So I can think of my j, my y component as being 0. And I have minus 2k, so I got minus 2 there. And now I take my dot product again, okay? So 3 times 1 plus -2 times 0 plus 6 times -2. 3 minus 12. So my dot product is -9. Okay. You might have heard me slip just now and call it an inner product. That's because this dot product, you know, it's got several names. I will probably slip up and call it an inner product a lot. And it's also called a scalar product. Okay. All of these would be correct. Technically, this is probably the best thing to call it. The dot product, so if you're interested, the inner product is a very general term that kind of applies to a whole range of things with similar properties. And this dot product we're learning is a special case of this inner product, okay? And then, the scalar product, that's just, another name for the dot product, okay? So you might, if you're looking at outside sources, you might see these terms as well. So don't be thrown by that. They're all the same thing for this particular case when we're working in the real numbers. Okay. All right. Where were we? Okay, so let's look at some properties of the dot product, and then we'll start looking at the meaning behind it. So this is the big one, okay? Property number one gets top billing. Let's say I have a vector A, okay, and I take the dot product with itself. So A dot A, okay? That is going to give me the length of A squared. So remember from 12.2, right? When I have a vector and I take its, it's not really an absolute value, but if I put absolute value bars around it, this is not an absolute value. This is telling me, I take the magnitude of the vector or the length of my vector, okay? Saying, these words are interchangeable for now. Okay. So what is this telling me? When I have the absolute value of a vector squared, that's the length squared of the vector. So this is length of A, and then I square it. Okay. And remember, the length of A, even though this is a vector, the vector's length, that's just a number, right? So when I square it, I'm just squaring a number. Okay. And there, we have a quick little proof of this. Okay, so let's, say we're working in R3. So my vector A has components A1, A2, A3. And let's say I take the dot product of A with itself. So A dot A, okay? So I would have this dot product here on the right side. Okay, well, what is this? I multiply A1 by A1 to get A1 squared. Then I add A2 times A2 to get plus A2 squared. Then A3 times A3, I add that there. Okay, so I get A1 squared plus A2 squared plus A3 squared. So that's just what this is. Okay. Now let's kind of work. So we've kind of shown what this is. Now let's try the other side. Let's figure out what this is and compare the two quantities. Okay. So let's look at the magnitude or the length of A squared. Well, remember what the length of A is, right? The length of A is given by this kind of distance formula, this sort of Pythagorean theorem. It's not the Pythagorean theorem, but it's, it's a direct result of the Pythagorean theorem, right? So the length of A is given by this, and then we're squaring it. So the square and the square root cancel, and I'd just be left with A1 squared plus A2 squared plus A3 squared, which is the same thing we had up here. Okay? So it must be that this is equal to that. So the length of my vector A squared is equal to A dot A. Okay. So this is a very useful idea. So I want you to get in the habit of whenever you see the dot product of a vector with itself, you should think not in the back of your mind, but pretty close to the front of your mind, I would say, if that's even a saying. You should kind of have at the tip of your brain that, okay, when you see a dot product of a vector with itself, we're talking about the length of that vector squared. Okay. You'll need that just a ton. And then the other properties are all pretty straightforward, and I think it'd be a useful exercise for you to check the rest of these, and we can do this in the same way we did with in the previous section. We did something similar, right? So for property number 2, for example, if you wanted to check this on your own, and then you can do something similar with the others, I would say, okay, let A be A1, A2, A3. And you can do this if you want to save yourself some time, just do it with A1, A2. Again, this stuff works in R2 as well. Let B equal B1, B2. And then figure out what both sides of this equal sign are, right? What would be A dot B? Well, that'd be A1 times B1 plus A2 times B2. And what's B dot A? Well, that's B1 times A1 plus B2 times A2. But really, okay, when we're multiplying two numbers in the reals, that order doesn't matter, right? So these two are the exact same. And then there's similar logic for all these other properties, and they're all important, okay? So we have, and again, these are kind of analogous to properties we see with arithmetic in R, right? When we're talking about addition and multiplication, we would say, we could phrase this as saying, okay, multiplication distributes over addition, meaning, okay, if I multiply, let's say I have a number x, and then I add y and z together, and I multiply by x. Well, that's the same as xy plus xz, right? And I'm just talking about regular multiplication here. So we might expect a similar property from our dot product, and we see that does indeed hold. And then similarly, we have, okay, this is scalar multiplication now, okay, and dot product, right? So when I have C, A without a dot, what's going on here? This C, this doesn't have a vector sign, right? So this is just a scalar. Remember how scalar multiplication works. I'm taking the scalar multiplication of C and the vector A, okay? And then I'm taking the dot product with the vector B, okay? And I want to point out, just to make it clear, when we have scalar multiplication, we're just going to put the letter or the number next to the vector. There's not going to be a dot, right? We're reserving the dot for dot product, okay? So this is scalar multiplication, and we get a result, and when we take that result and find the inner product with B, okay? So that's just what this left side is. And then try and parse what this right side would be, right, on your own, and how this is equal to this, and then this third side over here is equal to the other two. Another important property, if we take the inner product of the zero vector with any vector, the result is going to be the number zero. So again, remember, this notation is deliberate. This zero with the vector sign over it, that's the zero vector, meaning the vector of all zeros. And then what's this over here? Well, that's just the number zero, which is in R. So again, this is in what? This is a vector in R3. This is just a number in R. Okay. Now we can get into the idea of what the dot product represents. What is our interpretation of the dot product? We've seen how it works. We've seen some properties, but what is it? Okay. And we wanted to introduce how it works and these properties because it's having knowledge of like the mechanics of it are really going to help us get an idea of what it means geometrically. So we can think of the dot product between vectors v and w as kind of, I call it a weighted measure of the angle between v and w. Your textbook, I kind of added this word weighted here, but we'll see why I added that in a bit. But if for now you want to think of it as just a measure of the angle between v and w, that's fine. Okay. So when we take our dot product, that is kind of giving us an idea of the angle between v and w. So in R, let's say I'm in R2, I have this vector v, let's call that v. I have this vector w, okay. If I take the dot product, that should give us some indication about this angle theta in between v and w, okay. That's where we're going with this. We could also think of it as being a measure of how perpendicular or orthogonal these vectors v and w are. Okay, so that's kind of how I think of it. So again, I have vector v, I have vector w. I ask myself, how close are these vectors to being perpendicular at 90 degrees, right? You know, if I had vector w like this, okay, v has to be here to be perpendicular, right? So my dot product kind of tells me how close I am to being perpendicular. We could also think of it like that. And you know how you think of it I'll kind of show you both ways to think about it, and I'll let you guys make up your own mind about how you internalize that. So where are these ideas coming from? Why can we think of the dot product like that? Well, these interpretations really come from this theorem here. Okay, so let's look at that very closely. Okay, if theta is the angle between vectors A and B, then the dot product of A and B is equal to the length of A, or the magnitude of A, times the magnitude of B, times the cosine of the angle between them. Okay, so we see from this equality here, okay, when I take my dot product somehow includes some information about the angle between the two vectors. Okay, and let's kind of consider, you know, I'll be doing stuff in R2, and I'll kind of explain at the end why this works for any dimension. Okay, so but let's think about the plane R2. Okay, so let's fix our brains in R2. So let's start by considering vectors A and B, okay? And let's say they're both starting at the origin, you know, their bases are both at the origin, okay? So V goes out to here and W goes out to here. Okay. And again, dimension doesn't matter, but let's just think about this in R2 for now. Okay. Now, this is almost a triangle, right? We're missing the side that connects these two vectors to make the triangle. But let's first talk about what that side is. Okay. This is actually, and it might seem weird, this is actually, let me draw it. So we want to connect these two tips, right? And we can put the arrow, see, on this side. This is actually going to be the vector v minus w. Okay, that might seem very strange, but let's do this piece by piece. Okay, we'll leave that up there, but let's kind of start from scratch. So I had v and w, right? How does it work that this thing is v minus w? Well, this is kind of going back to section 12.2, our previous section. Okay, let's take a look at v minus w. Remember how we kind of found v minus w before when we didn't even have numbers, right? I would take this vector v, what would I do? I would kind of slide it over this way, right? If I did v plus w, that would be, I would put the base at the tip of v, right? V minus w is the same thing, except you could think of it as putting the tip of w at the tip of v. Okay, and then the vector v minus w, I would draw, let's see, I would draw from here to the origin, right? That would give me my v minus w, right? Okay, now remember that it doesn't matter this v minus w, okay, this vector is v minus w whether it's located at the origin or if I move it around my plane. So if it's down here, that's still v minus w. And look what happens when I drag it up here. It perfectly fits that side of the triangle, okay? So that's how I find that this vector here, this third side of my triangle, is v minus w. Okay. So now I have a triangle with three sides, right? I got v, w, and I got v minus w. So let's assume we know the length of v and we know the length of w. Can we find the length of v minus w without, without looking at the components of v minus w? Yeah, we could try Pythagorean theorem, right? But that only works if there's a right angle in that triangle somewhere, right? So if there's not, remember the law of cosines, right? That the law of cosines is kind of like a generalization for the Pythagorean theorem, but it works whether there's a right angle or not. So just a quick refresher. Okay, if I have a triangle with sides, let's say A, B, and C, well, C squared would be, let's say my triangle has lengths A, B, and C. Okay. So C squared would be equal to A squared plus B squared minus 2AB cosine of the angle between A and B, right? Okay. So now let's apply this law of cosines to our triangle with the vectors. Okay. Okay. So let's see, our vector v minus w, it should actually have base here and then arrow here. Okay, that's not going to be too important. What is the length of v minus w? What is the length of this vector? What is the length of this side of this triangle? Well, that length, the length of that vector, the length of that side of the triangle, however you think about it, it's this quantity, right? V minus w squared. Okay. And by the law of cosines, we know that this is going to be equal to this length plus this length. Okay, well, this length is magnitude of v squared. It's magnitude of v, and then we're squaring it. Okay, and this length here, well, that's magnitude of w, and then we're squaring it for our formula. And then I subtract this term here, minus 2 times the length of v, magnitude of v, times the magnitude of w, times the cosine of the angle between v and w. Okay, so we have this formula. On the other hand, think back to our properties. Okay, what did our number one property? What was our number one property? Remember when I have a vector dot itself, that's equal to the magnitude of that vector squared, right? You need to be able to think about it going the other way too. When you see the magnitude of a vector squared, you need to be able to say, hey, well, that's the same as that vector dot itself. Okay. So looking at this left side of the equation, I have v minus w squared, right? Well, that's the same as v minus w dot v minus w. Let's expand that, okay? And this, again, it's going to help a lot to know those properties, right? All those properties allow us to split up this dot product. Well, if you're good with these properties, you know that, okay, if I have a plus b, a vector a plus b dot c, okay, well that's the same as a dot c. Oh, you might be confused about why I did that. Let's say I have a plus b dot c. Well, that's the same as a dot c plus b dot c. Okay. That's essentially what we're doing here. Think about this as like foiling. You know, it's really pretty much the exact same as foiling. Okay, if these were just numbers, v minus w times v minus w, how would you foil it? It would be v squared minus 2vw plus w squared, right? That's essentially what we've ended up with here, just a dot product. Okay. So once we simplify, we see that this left side here is equal to this. Magnitude v squared plus magnitude w squared minus 2 times the dot product of v and w. Okay. So our law of cosines, this was our law of cosines. We expand this left side here, and we get this expression here. Okay. Now notice that this magnitude of v appears on both sides, magnitude of w appears on both sides. So let's just cancel those out. And what are we left with? We're left with this equals this. Okay. So negative 2 times the dot product of v and w equals negative 2 times the magnitude of v, magnitude of w, cosine of the angle between them. And then all I do is I cancel out those v and w's. And what do I see? I see v dot w equals magnitude of v, magnitude of w, cosine of the angle between them. So take a minute to digest that if you need. Continuing on, you know, this is why I say this is why I said up at the kind of beginning of this section, our interpretation. We can think of the dot product as a weighted measure of the angle between v and w. Okay. So what do I mean by weights? This dot product, you know, it's not just the cosine of the angle between them, right? It's the cosine times the magnitude of v and the magnitude of w. So these magnitudes are kind of like weights. So the bigger the vectors are, the more their magnitudes affect this number, right? You know, the angle, it doesn't matter. Let's say I have vectors v and w and they're this long, right? All right, I get one dot product. But then if I did this, I had the same angle but longer vectors, I would get a different number for my dot product, even though the angle between them doesn't change. Okay, so this number is kind of affected by the lengths of v and w. Don't worry how that relation works, but just know, really you just need to know this equation here. V dot w equals magnitude v, magnitude w, cosine theta. Okay, and then an important note, what if I want to find the angle between two vectors, right? I could rearrange. If I can find their dot product, I know the v dot w equals this, and I rearrange, I divide both sides by these. These are just numbers, right? They're just scalars. So we divide both sides by these, and then I get cosine by itself. And then maybe I could take inverse cosine to get some idea what the angle between the vectors was. So let's try that. Let's try and find the angle between these two vectors in R2. So angle, or vector A, which is 4, 4, and I didn't give this a name, we can call it B, 0, 7. Okay. So first, what would that look like? Okay. And I picked one that, you could figure this out fairly easily if you think about these vectors. You could figure it out without doing dot product really. Okay. So let's see, 4, 4, that's like, let's say that's here. Okay. Boom. I'm not going to draw it too carefully. Boom. And then 0, 7, well, that's just like out here, right? Oh, wait, no. That'd be up here. All right. Maybe we should do these in blue. Okay. So let's say that's my A and this is my B. What's the angle between them? Okay. Well, let's use our formula. I know A dot B is going to be magnitude A, magnitude B, cosine theta. So let's first figure out everything we can. What's A dot B? Okay, A dot B would be 4 dot 0, 7. Okay, and then what's magnitude of A, magnitude of B? Let's figure those out to the side over here. Magnitude of B is really easy, right? When I have, a vector that only has one component, the length of that vector is just that number. Okay, and you can try this. Plug this vector into our distance formula or our magnitude expression, and we'll see that the length of the vector B is just 7. Okay, boom. Okay, so this is equal to 7. Boom. What's the magnitude, or what's the length of magnitude of A? Well, now I need to use that formula, right? Magnitude would be 4 squared plus 4 squared square root. So square root of 32, which is, what is that? 4 square root of 2. Right, yeah. So the magnitude of A is 4 square root of 2. And then, let's write that a bit neater. And then multiply by cosine of the angle between them. Okay. So what's this left side? Let's simplify the left side. It's 4 times 0 plus 28, right? 4 times 7, 28. So 28. And then on the other side, I have, let's see, 28 square root of 2 cosine theta. Simplifying, I have 1 over square root of 2 equals cosine theta. This might start looking familiar now. This is the same thing as square root of 2 over, square root of 2 over 2, right? Yeah. Okay, so what angle has cosine of square root of 2 over 2? This, let's see, the angle would either be pi over 4 or, negative. There's a couple ways to write it. It would either be this angle here, pi over 4, or negative pi over 4, etc. But really, we're not talking about the angle with relation to the x-axis. We're talking about this angle here. Okay, so really, just confine yourself to when you're doing this process, your angle should be positive. So ignore the negative angles, right? Because when we're talking about the angle between two vectors, okay, that angle is always going to be positive. Okay, so I wouldn't want to say negative pi over 4. It's just pi over 4. So what we've discovered is that this angle is pi over 4. And then this technique can be used to find these things called direction angles, which is something in your book. And, I didn't know the term, or I didn't remember the term until I refreshed it. Not to say it's not useful or anything, but it's, I wouldn't say you would commonly see it in upper level courses, things like that. I mean, you definitely might need it for real world applications and things like that. You know, angles are important, locations of objects, things like that. So what are these angles? This is why I say apparently, because this is something I didn't remember. Alpha is the angle if we have some vector in R3, okay? So now we're talking about R3 in particular. Alpha is the angle that vector makes with the x-axis. Okay. So let's draw R3 real quick. Where's my ruler? Come on. It's weird. Okay, so we have our R3. Let's say I have a vector, let's draw in green. Let's say I have this vector that's coming out this way. Okay, and let's say, okay, let's kind of draw it kind of nice so we get an idea of where it's going. Let's say I draw it down to, okay, this is where it hits that horizontal plane. Okay, so maybe you can see, well, it's coming, you know, this way along the x-axis. Remember, this is x, y, and z. Okay, so what's the angle it makes with the x-axis? I want to find the closest angle to the x-axis. So this is, you remember, this is kind of a line, a shadow in the xy plane. Okay, so this would be the angle with the x-axis, right? So that's my alpha. Okay. On the other hand, this, the angle it makes with the y-axis, that'd be my beta. Okay. And then finally, okay, this, the angle here from the z-axis to my vector, that's my gamma. So those are the direction angles. Hope I'm not giving you a headache. Okay, so those are our direction angles. So if we're given a vector, can we find the direction angles? And yeah, it's pretty straightforward. And now that comfort with the ij and k notation will come in handy. So it's a very similar process to what we did here, finding the angle between two vectors. Okay, it's just a special case of that. I want to do the exact same thing, okay? But if I want to find, let's say I'm given a vector, I'll do a quick and ugly R3. Let's say I have this vector here, okay, and again, it's R3. Let's say I want to find the angle with the x-axis, right? Okay, well, what two vectors should I find the angle between? I should use my original vector. And what's this vector? I could call it, actually, so instead of doing this vector, I'll do the unit vector in the x direction. I'll do this vector here, which goes out a distance of 1. Remember that we call that I. So if I do the dot product of this vector I with my original vector, let's call it v, okay, that will give me a clue about what the angle between the x-axis and v is. Okay, so alpha, that angle, okay, what is that angle? That's what we're looking for, right? I know that v dot I is going to be equal to the magnitude of v, magnitude of I, cosine of the angle between them, right? And that angle between them is alpha. So what is my v dot I? Well, let's say, let's be specific with v. Let's say v is equal to, that looks something like -2, 2, 2. Let's call it that. Okay, so what is v dot I? v dot I would be negative 2, 2, 2 dot, what's I? 1, 0, 0. Okay, so that's just negative 2. Okay, so that's my left side. And then on the other hand, I have magnitude of v, magnitude of I. Well, magnitude of I is just 1, isn't it? So I have 1. What's magnitude of v? It would be square root of 12. Try that on your own, find that on your own. And then I have cosine of alpha. Okay. Now let's just simplify this. Square root of 12, that's what? 2 square root of 3 times 1. Okay. So I have 2 square root of 3 cosine alpha equals negative 2. Okay. Getting cosine by itself, I get 1 over square root of 3, negative 1 over square root of 3 equals cosine of alpha. And then, let's see, simplifying. It's probably not going to simplify nicely. This is the same thing. So my angle alpha would be cosine inverse of square root of 3 over 3. So doesn't look like it's working out nicely in this one. But this is an acceptable answer. If you plug this into your calculator, you'll get something. You'll get an answer, and that would be our angle. Oh, and I just realized I dropped my there should be a negative sign here. Okay. And when I plug this into my calculator, I get the angle is 125 degrees. Okay. So the angle from this positive x-axis to my vector. Okay. So that's actually how I should consider my alpha. That would be 125 degrees. Okay. If I wanted to find the angle between my vector v and just its closest angle to the x-axis, so like the angle from here to here, the vector I would have used would be negative I, so negative 1, 0, 0. Okay. And then repeat the same process. So we did direction angle for the x-axis, and then y-axis, z-axis, same things. So now we can talk about the numerical values of our dot products. Okay, so let's assume I have two vectors and I take their dot product. Usually the dot product is a lot easier to compute than just this thing here. So for example, if I have 7, 1, 4, and 2, 5, 6. Okay. Finding this dot product is pretty easy, right? It's just 7 times 2 plus 1 times 5 plus 4 times 6. Okay. So that's the dot product. On the other hand, this thing it should give us the same number, but calculating it this way would be pretty difficult, right? Because I would need to first find the length of this vector, then the length of this vector, and then I would have to know the angle in between them, right? So this form is harder to find. So we need to be able to calculate v dot w directly, just using this, and then we would like to be able to interpret the number it gets out, right? Without finding length of v, length of w, and then dividing and all that. So we'd like to be able to look at this number here directly and kind of get some information about the angle between my vectors. Okay, so we can't get too specific, but we can at least get some general information. Okay. So let's say I take the dot product of v dot w and I compute this. Okay. And that number is greater than 0. What does that tell me? Okay. So remember, v dot w is the same thing as magnitude of v, magnitude of w, cosine of theta. Now this is a length, right? And this absolute value bar, it's not an absolute value, remember, but it's got a similar property that this magnitude of v, that's always a positive number. Okay, it's positive. So, and so is magnitude of w. Any magnitude we take is going to be positive. Okay, so I have a positive number, okay, and then on the other side of my equation, I'm saying, okay, v dot w, that's positive, right? So the result is positive. So I got a positive here, and then on the other side of the equal sign, I got a positive, positive, and then I see, okay, well, what's this cosine of theta? Well, to make sure that this left side is positive, this cosine of theta has to be positive as well, right? Okay. Sorry, if you were looking at that, you can go back and pause. No, we're just looking at that. So what we've found out is that cosine of theta is positive. The cosine of the angle between these vectors is positive. What does that mean? And let's just work in R2 for a second. That means my angle is somewhere in here, right? And really, that we should always kind of consider it as a positive number. So really, my cosine, my angle is somewhere in here. Okay, that means my angle between my two vectors is between 0 and 90 degrees. It's between 0 and pi over 2. Okay. So that's a pretty big piece of information, right? I see my dot product, and I can, if the dot product's positive, then, and actually this should be greater than 0. Okay. If my dot product's positive, then my angle is somewhere between 0 and 90 degrees, 0 and pi over 2. Okay. So this kind of means we could also think of this as saying, okay, if that's my V and my W is less than 90 degrees away, okay, so maybe it's here, they're sort of pointing in the same direction, right? They're kind of both pointing, up and to the right, basically. So that's kind of a way we could think about this. Call it same direction-ish. On the other hand, let's assume the dot product is negative, okay? I do kind of a similar thing, okay, I got v dot w, and then on the other hand, I got, all right, magnitude of v, magnitude of w, cosine of theta. I'm saying that this number over here is negative. Well, this is positive, so that means this cosine has to be negative, right? So what does that tell me about my angle between my two vectors? It has to be, let's see, cosine is negative when we're over here. And again, let's assume, our angle is positive, okay? So our angle has to be somewhere between 90 and 180 degrees. So again, if the cosine is negative, then we would expect that our angle between our two vectors would be somewhere, between 90 and 180 degrees. So for instance, if, that's my V, my vector W, let's say that's 90 degrees away from V, and that's 180. My vector W, I would expect my vector W to be somewhere in there. Okay. Now, this doesn't mean like we have to be moving counterclockwise. Like for instance, my vector it would kind of end up being the same thing. But let's say I was measuring this way. Again, expect my vector to be somewhere between let's see, oh, 90 and 180 degrees. Okay. So really there's a couple of possibilities. Maybe my, vector v and w are kind of oriented this way, or maybe w is coming off. So maybe my vector w is in here, or maybe it's in here. Okay. But either way, if I kind of measure the shortest distance, shortest angle between v and w, I would expect that to be somewhere between 90 and 180 degrees. Okay. Now, what happens if v dot w is equal to 0? Okay. Well, then there's only one possibility. V and w have to be perpendicular. Okay. So let's see. So again, I have v dot w is, we're saying that's equal to 0, right? Then on the other hand, I'm saying, okay, well, that's equal to magnitude of v, magnitude of w, cosine of the angle between them. Okay. And we're assuming that we got two non-zero vectors, right? We're assuming that this is positive, this is positive, right? These can never be negative. They can be equal to 0 if the vector we have is the 0 vector. So we're kind of assuming that neither of these is the 0 vector. Okay. Well then, for this to be 0, for this side to be 0, and this positive, that means that this cosine of theta has to be 0, right? Well, when is cosine of theta 0? That's at 90 degrees, right? Pi over 2. All right. So this is telling me my vectors v and w have to be exactly 90 degrees apart. So if v is here, that means my w either has to be here at 90 degrees, or maybe it's here at 90 degrees. It doesn't matter which one it is. I know the angle between them is going to be exactly 90 degrees. Okay. Now, when two vectors are at 90 degrees from each other, you might be used to the terminology perpendicular. We would say v and w are perpendicular. And we'll see that terminology in the course. But a term you'll start seeing more and more if you continue in math is orthogonal. Okay. Now, in this case, it means the exact same thing. These terms are interchangeable. Again, this perpendicular. We can kind of think of this as being a special case of the term orthogonal. For now, I'm not going to get into what the subtle differences between these terms are. Think of them as synonyms. Okay, so the book will start saying, okay, v and w are orthogonal. Okay, and just think of that as being perpendicular. And in fact, we have this theorem, and the book gives us this nice theorem that okay, v dot w are orthogonal if and only if v dot w equals 0. Okay. What does this phrase "if and only if" mean? Think of it as two different statements. Okay, when we say if and only if, that's the same thing as giving these two separate sentences. On the other hand, we could say v dot w equals 0 implies v and w are orthogonal. And it also implies the opposite. So we can combine these two sentences into one using this terminology here, if and only if. So we've seen a way to nicely interpret v dot w, but we could also think about how, a bit more closely, how these two quantities, v dot w and magnitude v, magnitude w, cosine theta, are related to each other. So what if we do the dot product of v and w, and we take their magnitudes, and we see that we have this relation here, that, well, the magnitude of v dot w, or excuse me, the number I get when I take v dot w is exactly equal to the magnitude of v, magnitude of w. Well, that would mean, you know, I should have a cosine of theta here, right? Well, if cosine of theta is 1, okay, that's kind of the situation we're in, right? We have, by implication, we got a cosine theta here. If these two things are equal, that must mean that cosine theta is equal to 1, okay, which is what I've stated here. Well, then what's the angle between my two vectors? It's got to be 0, right? Okay. So v dot w are parallel and they point in the same direction. So what's an example of that? Let's say I have vector v going this way, and I take the dot product of v dot w, I got another vector w, I take their dot product, and I see we have this relation here. Well, that means w has to be along that same line, pointing in that same direction. Now, maybe the lengths are the same, but they're going to be along the same line. So maybe v only goes out this far, and then w goes out a bit further, but they're along the same line and pointing in the same direction. Okay. On the other hand, what if I have v dot w is equal to the negative of their magnitudes? Well, by implication, again, I have a cosine theta here, right? There's a cosine theta here by implication. And if there's a negative sign, it must be coming from this. Okay, so what we're saying is that this cosine of theta must be equal to -1. Okay. So what's my theta then? Well, it's got to be pi. So in this case, my vectors are along the same line, but pointing in different directions. So maybe my vector v goes off in this direction, and my vector w, it's along the same line, but it maybe goes off in this direction. So that's how those dot products and these two expressions of these dot products are sometimes related to each other. Before we cover projections, I said that I would briefly talk about, you know, we were doing everything in R2 and maybe a little R3, but I said it works in Rn, right? Why do these dot products, why do these formulas hold in Rn as well? So maybe you're used to thinking of, and maybe even more generally, you're used to thinking of like angles in 2 dimensions, 3 dimensions, so on. What does it mean to have an angle of 20 degrees or 50 degrees in, you know, 8 dimensions or so on? The key idea here is that when I have two vectors, it doesn't matter what the dimension is, I can always make like a 2-dimensional triangle between them, okay? And we can see that in R3. If I have two vectors in R3, let's say I have v coming this way, and then, you know, w going that way, okay? it might be weird to think that I can draw a triangle between the, like a two-dimensional triangle whose two sides are these two vectors, or two of which is sides are these two vectors, but we can, right? So let's say I have, this is my triangle, these are my two vectors. How can I draw a triangle with these two vectors? Well, I just connect their ends, and it doesn't matter how it's oriented in space. I can always do that. And the same is true in four dimensions. We can't draw four dimensions, obviously. But if we think about R4, at R, there's still an origin point in R4, right? A point where all the coordinates equal 0. I'm not going to try and draw axes. And then I have two vectors in R4. Maybe, and let's say they're both starting at the origin. So I have this vector V and this vector W. Okay, and imagine these kind of floating in this four-dimensional space. I can always draw a straight line between their points, right? And that straight line will always be a triangle. So I can, and then, once we have that triangle, well, this triangle is just a two-dimensional figure, right? So I can use my same ideas of angles and stuff like that from R2, okay? So I still can find this angle between these two vectors, okay? So this idea, now, on the other hand, v dot w, that's got like four components now, right? It's v1, v2, v3, v4, dot w1, w2, w3, w4. So when I take the dot product, now I got a sum like this. Skip some steps. Okay, but it's still got this same relation. On the right side, we can still say that's going to be magnitude of V, magnitude of W, cosine of that angle between them. And again, that angle between them is still the same concept of an angle between two lines we had in R2. Okay. So it scales up to higher dimensions easily. Okay. So that's why it works. It continues to work in higher dimensions. Now, again, don't freak out about higher dimensions. This book is like 99% in R3, R2, and R3. Okay, I just want to make you guys aware of these ideas as I see them. All right, now that we have developed the dot product and we have a little intuition about what it means, we can talk about projections, which are just hugely important. Again, this is something that if you're going higher in math, like linear algebra and beyond, you would be doing all the time. And they have a lot of applications that really show how important these dot products are, where they're used in very important fields like data analysis, machine learning. Pretty much any type of applied math is going to use some sort of projection. They're really good for like if you've heard of like least squares and things like that. They're really good at those methods for finding, I'll say, an approximation to something. I won't talk too much about these applications, but like I took a machine learning massive data course a couple semesters ago in my grad school, and like the first thing we learned was the most basic method was using dot products and projections. So it continues to be useful. All right. Now that I've thrown around the term projection a lot, what is a projection? Okay, and again, let's kind of flip it from last time. let's start with the idea first and then get into the mechanics of it. So let's say I have v, two vectors v and w, and I want to find this thing called the projection of v onto w. Okay, so what is that? Let's say I have v, and what I'm going to do is I'm going to take like my ruler, and I'm going to put it at 90 degrees to my not to any axis or anything, but to my vector w. Okay, so this is pretty much perpendicular to my axis w, right? It's like 90 degrees, let's say. Now, what I'm going to do is I'm going to kind of draw a line from the tip of V. Let's say, okay, I just erased it a little bit. Let's say the tip of V is here. Okay. What I'm going to do is I'm going to draw a line from the tip of V along that 90-degree line down to W. Okay. Now, this vector here, okay, that goes along W and stops here is the projection of V onto W. Okay. Another way to think about that is, okay, let's say I had these vectors V and W. Let's say I ignored the axis, I just took these. Okay, and then I kind of, let's see, can I rotate on here? No, I can't. Okay, I'll try and explain this without rotating it. So focus on the vector W, okay? And let's imagine that directly, let's kind of imagine that W is like the surface of, some flat planet, okay? And, or, whatever, just a flat piece of land, okay? And directly overhead from W is a sun, and it's shining down, okay? And it's like, let's say it's like high noon, okay? So the sun is directly overhead, okay? It's shining down, it hits this vector V. Where would the shadow be cast onto W? It would just like go straight along this line to here, right? So that's kind of how I think about projections. Like if I had like a light source, kind of going back to our original drawing now. Okay. Oops. If I had a light source that was directly over W, directly over W, hitting it at a 90-degree angle, right? So boom, 90 degrees. What kind of shadow would it cast? What kind of shadow would V cast on that vector W? Well, my light source would cast a shadow here, okay? And then if I had the vector that was everything up to, okay, that line, that would be this vector, right? Okay, so that's the idea of what the projection is, okay? It's like we're projecting V down onto W, okay? So it's fairly straightforward terminology. Okay, so that's the idea of what it is. How do we find it? Okay, and this might be a good time to review unit vectors, which we touched on briefly in 10.2. Okay, remember a unit vector is any vector of length 1. Okay, so let's say I have a vector, and it doesn't matter what direction it's pointing. Okay, let's say I have a vector v. Okay, and let's say it's like 4.5 units long. Okay. Well, there's a unit vector in that direction, right? There's a vector that's pointing in that direction that has length 1, right? So let's call the bigger vector v. And let's call the smaller vector, you know, well, how could we find that smaller vector, right? Let's say we know the components of V. Let's say I know V is equal to V1, V2. Let's say I want to find the components of that unit vector that's pointing in the same direction. Is there a way to take these components and scale them down to get a unit vector? Yeah. What I do is I first figure out what the magnitude of V is. All right. Well, that's what? Okay. All right. But let's just think about it like this. If I take the components of V and divide by that, that's going to turn my thing into a unit vector. Okay. Now this is a vector. It's got two components. They're slightly smaller than these components, right? And we could abbreviate this whole thing as V over magnitude of V, right? Well, it turns out that this V divided by its magnitude will always be a unit vector pointing in the same direction. Okay. So for example, let's continue on with unit vectors for just a second. Oh, looks like I got space for an example here. Let's say I have the vector V equals 4, 7, 2. Okay. So in R3, just doing a quick ugly sketch. What would 4, 7, 2 look like? Well, I'd come out 4 units this way. 1, 2, 3, 4. I'd come out 7 units this way, boom, and then 2 units up. Okay, so it looks something like, it'd be like here. All right, it'd be a bit above the plane. Okay, so I'd have like, this would be my vector. Okay, so it'd be something like that. Now, let's say I want to find a unit vector pointing in that same direction. Okay. Well, it should be V over magnitude of V. Okay. Well, what is the magnitude of V? So that's what? 53 plus 16, 69. And that worked out. What is, no, so that's not a nice square root, is it? Let's see. Can I divide by, no, it's not. So if it was 169, that would have worked out nicely. Okay, but it's not. So the magnitude of V is 69. So if I take the components of V and divide by that magnitude, so 4 over square root of 69, 7 over square root of 69, 2 over square root of 69. This thing is now a unit vector pointing in that same direction. Okay, so that's an important concept, and being comfortable with that will help in this next bit. Okay, so now that we're reacquainted with this idea of unit vector, let's go back to the projections. Okay, so I make my projection, okay, and it's basically this vector, right? I want that starts at the origin, goes along W and stops there, right? So I want to find that vector. Well, let's think about this. Let's think about the unit vector along W. Let's say W is like 8 units long, right? Well, there's a unit vector down here, right? That's 1 unit long, pointing in the direction of W. Now, if I could find out, um, some sort of scaling factor, maybe like how long this vector was, okay? How long the projection was. I could just multiply the components of the unit vector by that factor, and that would give me a vector that was my projection, right? It would stop there. Okay. So that's kind of what we're doing. We're looking for some value, to multiply that unit vector by. Now, what is that unit vector? Remember, that unit vector would be W divided by magnitude of W, right? Okay. So I need to multiply W over magnitude of W by something to scale it up. Okay. So really what I need to do is I need to find this length, right? I need to find that length. Well, I know what this length is, right? That's my length of V, okay? And then if I consider the projection stopping in there, okay, this is our right angle, right? Okay, so this is the hypotenuse. This length V is the hypotenuse of a right triangle. So if I multiply V by this angle here, that should give me that length, okay? But what is this angle here, okay? Remember, that angle, let's see, is related to my dot product, right? I have V dot W equals V W cosine theta. And actually, I don't even, I was trying to walk it back through the dot product formula, but I don't even need that, right? The cosine of that angle is V, no, excuse me, it's that projection. It's my projection I'm looking for. Let's call it P, okay? That's a number, okay? That cosine is going to be P divided by length of V, all right? And on the other hand, this cosine of theta equals V dot W over V, magnitude W. Okay. So now forget about this cosine theta in the middle. We have, my P is what I'm trying to find. I have P over magnitude of V equals this thing over here. So that length of that side must be equal to magnitude V dot W over magnitude V, magnitude W. Okay. These cancel, and I'm left with that length I'm looking for is V dot W over magnitude W. Okay. So that's the scaling factor I'm looking for. So if this is just a number, right? I plug all this in, I just get a number. If I multiply my unit vector, W over magnitude of W, by that P, I'm going to get my projection. Okay, so that will give me my projection. Now, that was all very complicated and convoluted. If you could follow along, great. What it boils down to is that vector, that my shadow, okay, my projection of V onto W has this formula. Okay, I take the dot product of V and W. I divide by W, magnitude of W, and then I multiply that by this unit vector. So this is a number, this is a number, that's a vector. So I get a vector scaled by some scalar, right? Okay. So this is my formula for the projection of V onto W, which we typically write, the projection of V onto W, we usually write like this. Okay, so PROJ subscript V W. Actually, you know what? That's backwards. If I want to project V onto W, I put the thing I'm projecting onto in the subscript, and I got this. Okay, and we could rewrite this. Another way to write this formula is like so. W, in my denominator, I have magnitude of W times magnitude of W. Well, remember what magnitude of W squared is. That's the same thing as W dot W. Okay. And this is the form I use. That's the formula I remember, but you do whatever's right for you. All right. So that's the projection of V onto W. And the book makes the distinction between, the book calls this the vector projection, okay? So this is a vector, right? Because this is a vector and then this is some number, right? So the result is a vector. So this is a vector, so we would, the book makes the distinction of calling this the vector projection of V onto W, okay? The book also has something called the scalar projection, which is just that number we multiplied our unit vector by. And remember what that was. We found that was this, V dot W over magnitude of W. Okay. Okay, so we call that the scalar projection of V onto W. And then we have a similar notation for that. It seems that it's comp W V. Okay. This notation is, I've seen it before, but it doesn't pop up a lot. This this notation of projection, that's very common. Okay. So get used to that. All right, let's try an example real quick, and then we'll finish the video. So let's say, just make something up. Let's say I have vector 1, 4, 6, and W is equal to about -3, 3, 3. Okay. Let's find our projection of V onto W. Okay. So by my formula, I know that's going to be, again, the form I use is this. Okay. So we know what W is. So really what we got to find is this number that's out front. Okay. So I need to find V dot W and W dot W. Okay. Well, V dot W, that's what? 1 times -3 plus 4 times 3 plus 6 times 3. So 12 plus 18, 30 minus 3 is 27. Okay. What's W dot W? Well, that's going to be 9 plus 9 plus 9, 27. Well, isn't this working out nice? Am I doing everything correct? 12, 18, 30, minus 3, 27. Yeah, okay. So I just randomly picked numbers that cancel out. 20. So v dot w over w dot w is 27 over 27. And then I multiply by the vector w, right? Which is negative 3, 3, 3. So this is my projection of v onto w. Okay, simplifying 27 over 27 is 1. And I just end up with that same vector w. Let's see one more example where the numbers don't work out nicely, or as nicely. Let's do v equals 9, 1, 6, and about w is equal to 0, 0, 3. How about that? Okay, so let's again find the projection of v onto w. Okay, that's going to be v dot w over w dot w, w. Okay, so let's find v dot w. That's 9 times 0 plus 1 times 0 plus 6 times 3, 18. W dot w, that's just 9. So v dot w over w dot w is 18 over 9. Then I multiply by my vector w. So I get 2 times my vector w. Okay, so I just take my vector w and multiply by 2, scalar multiplication. And the result is the vector 0, 0, 6. So that is my projection of v onto w in this case.